Hi everyone, this is going to be a very short lecture about the second derivative test, which is stated here, and we're not going to prove all those three cases, but we're going to look at just one case and show how the proof goes, and then that'll explain how the other two parts of the proof actually go. So it has everything actually in it. So let me first explain about this condition. These a, b, c are the coefficient of a quadratic polynomial where they satisfy this condition. So you might have recognized this number b squared minus 4ac. Indeed, they are it is the discriminant of a quadratic polynomial. So what we have here is that if we have this discriminant less than 0, and if the coefficient of x squared is positive, then this quadratic polynomial ax squared plus bxy plus cy squared will remain positive all the time, no matter what you plug in x and y. Unless if they're both, the input x and y are both 0, then it is going to assume 0. And except that special case, every number you put in here will remain positive. You can experiment with x squared plus 0 times xy plus y squared. That's a simple example for which this one is satisfied. Alright, so we have that lemma. And this lemma just simply uses very simple algebra that you learn any beginning algebra course. So the problem we have here is the following. So we're going to use that lemma to prove the following special part, the one part of the second derivative test. We assume this standard condition, so the second partial derivatives, f of x, y, are continuous, not just exist, it's continuous. And then another thing is that the partial derivative at a given point, a comma b, are 0. So x partial and y partial is 0. Then this is a condition about the second derivative. If this second derivative condition is satisfied, that is kind of comparable to this discriminant condition. It's quite in the same shape. There's a square and then product of two numbers. So if this guy is a positive, and if xx, the second derivative value, ab, is positive, these both are positive, then all directional curves at ab have a local minimum at that point ab. So what we mean by the directional curves is that this f of xy is specialized at this line. That's a line which is actually not arbitrarily parameterized, but it's an arc length parameterization at that point a comma b. So what this means is that if you cut the graph, the surface of z equals f of xy along the direction, whatever that direction we're looking at, if you cut it, it's going to create a plane curve, and that curve always have a local minimum at that point. So I'm going to bring up the class notes and how we explained, and there are lots of parts of this explanation, but for your proof you don't have to state all the explanation. So be able to distinguish which part is a proof and which part is just an explanation for you to understand the context. So this is a part from the board that this is not going to be part of your proof. It's just look at this to understand the beginning part. First of all, if you were looking at the local extremum value, local maximum minimum at certain point like a comma b, and it has to be the case that the derivative must be 0. It's because this is a very special directional derivative. This along the x-axis and along the y-axis. Of course, if you cut it, if it is a local minimum or maximum as a two-variable function, it is going to be local maximum or minimum as one variable function. So if you're looking at the section along the x, it's going to be one variable function, and by Fermat's theorem, the derivative is one variable function along that direction, it must be 0. Whatever the other direction you see, it must be 0. So this line is explaining local extremum condition forces this first order derivative to be 0. But not all the first order derivative 0 correspond to the local extremum, and the saddle point is an important example of that. So I'm showing here the saddle saddle shape, and this is a surface. I hope you recognize this as a three-dimensional shape. It's sitting inside three-dimensional space. If you look at cut along the x-axis, which is this part here, looks like, sorry that I'm mixed up here with these coordinates, but it looks like a local maximum. But if you cut it the other way, it looks like a local minimum. So these are the two sectional or directional curve along the x-axis and y-axis. But if you look at the partial here and the partial there and derivative there, they're all zero. So having derivative 0 in here and there doesn't guarantee that as a two-variable function, the function is having a maximum, local local minimum. So that's what I mean by, that's what this statement is about. If you have a local extremum value at a comma b, for example, then we have a partial 0. But this partial, first partial being 0 doesn't mean it's a local extremum. So this this sensitivity is true for the one variable case as well. So we need something else, more some other condition that guarantees extreme value, and this is not enough. So our test consists of we have this condition as a necessary condition, and what could be another one that kind of guarantees an extreme, the existence of a local extremum, not that saddle point shape. So let me show you what to prove here again. Lots of things given. We have the first partial derivative value set to be 0, and then we have some inequality positive conditions here. But what we are asked to prove is this particular curve. Z is usually, we started with a two-variable function, but x and y are parameterized. Some line parameterization, arc length parameterization of a line in xy plane that passes through given points a comma b. So that's where we should start. We got a handle on that zt as a one variable function, and then think about how to show this one is actually local minimum. So that's the curve here, and that's what we mean by directional curve. And this directional curve, we have to show it has a local minimum. So let's start from here, and this is going to be the beginning of your proof. So this is the beginning of the setup. So it's about a line, arc length parameterization of a line that passes through point AB. So here's your point AB, and this is some arbitrary line. It passes through that point A comma B in the xy plane right here. An arc length parameterization requires this directional vector to be a unit vector. Okay? So we have this directional vector alpha comma beta, and its length is 1. So if we use this directional vector and parameterize this line, and it's going to be nice arc length parameterization. And it's a standard thing that we set this base point a comma b as a t-value 0. So we practice a lot. That line here is given by following parametric equation, x and y, starting from a and b, in its directional number, alpha and beta, multiplied in front of t. And that's going to be the arc length parameterization of a line that passes through point a comma b. So originally z is f of xy, two variable function. With this composition, z is going to be one variable function. But what it means in that geometrically is that there is going to be a plane that is extending this line in a perpendicular to xy plane, and that plane is sketched here. It's not necessarily any plane that is parallel to the coordinate planes yz or xz. It's just some arbitrary direction. But if you cut the surface, it's going to create this curve, and that curve relative to this t-axis I created here is given by this formula, z equals zt. So we have a formula, it's all abstract, with a little bit of a specific part here about x and y. We want to show this z of t, one variable function, has a local minimum. So I realized I need to clarify and add this part to our slide, so I wrote extra things. So recall the one variable situation. Z is now a function of t, one variable, and we want to establish the z of 0, that's what's happening over the points a comma b, just along that direction alpha beta, z of 0 is a local minimum. We want to establish that, and one of the sufficient condition to do that from Calc 1 is a derivative at that point is 0. That's not enough to conclude it's a local minimum or maximum, but there's a second derivative test condition for one variable. If the second derivative value at there is a positive, it guarantees that it's a local minimum. So first let's show the z prime of 0 is 0. Right, let's start from here. Z is a two-variable function, and z now x and y, the two independent variables, are composed like this one variable function, and we're about to differentiate to say something about z prime of 0. That's exactly the chain rule. So we need to apply the chain rule to this part f of x, y, where x and y are composed with one variable. So when you do this part in your calculation, try to write down just a bit more than what I have here, and that makes a proof. So z of t is the derivative with respect to t, and the chain rule says first you start with a partial with respect to x, then what you have to multiply here is the x derivative of x with respect to t. Now if you go back and look at the formula of x, it's a linear in t, so if you differentiate you only get alpha and there's no t factor kicks in. And there's fy times dy dt, and again y is given by a linear formula, so only you have beta here and there's no t part kicks in. So that's the general formula of a derivative, but what we wanted is a z prime of 0, not this general formula, z prime of 0. Now as t varies, and this one changes, but when t equals 0, that part picks up a comma b. But the part of the condition, the partial derivative at a comma b, it's 0, and partial derivative a comma b of with respect to y is also 0. So they too, whatever that alpha and beta is, they're always a 0. Therefore, the z prime of 0 is going to be 0 all the time. So that established the first part we wanted to show. Now the first part we wanted to show is this one, z prime of 0. So we have that part. So next part is to show that z double prime is a positive. Then that directional curve we have has a local minimum. Okay, I guess the main motivation in me forcing you to learn this whole thing is basically about this second derivative part. So I want you to do this part carefully. Let me get more space out of here. Right, here it is. We have the first derivative calculated in terms of t, but this fx is mainly in terms of x and y, where x and y are composed in terms of t here. So to get the second derivative of z as a function of t, we have to differentiate this one. Notice that alpha and beta was really the constants because x and y composed as a function of t is a linear function. But this fx and fy still has x and y in it, and they're composed with respect to t, so that's going to be the main part we have to be careful about. So we're applying this alpha and beta is constant, so we're not touching that part. We're not doing any product rule or anything. It's just a constant. So we have to differentiate this fx and fy with respect to t. Just like we did to f of x, f of xy, we have to do the same thing. This whole thing, f subscript x, take that as a compound name of a new function and do exactly the same thing we did. That function differentiated with respect to x, multiplied by dx dt as I wrote here, and the same function differentiated with respect to y and times the dy dt. So that's how you're going to do the chain rule to this new function, which still has x and y composed with t in it. So that's how it's going to look like if you apply the chain rule to fx. Let's do the same thing to fy. Then fy is there with respect to x and dx dt. And fy differentiated with respect to y and dy dt, which is beta. And beta is still out there as a constant. So this is the important part. If you have to spend time and to do any part rigorous and careful, and this is the part you have to focus on. And this whole thing is mainly about to understand the shape of the second derivative along that line with the direction alpha beta. So we have this, and if you simplify it and just look at it as a function, because function of alpha and beta. So what is varying here overall is different directions. But right now, everything here is a function of t. So we're going to eventually plug in t equals 0, then alpha and beta is constant. So you don't have to do anything about this part. But as we plug in t equals 0 to all this fxx part and fxy part, they just pick up a comma b if you look at the parameterization of x and y. Okay, so I summarize it here more nicely. So we looked at that raw expression of the second derivative of z as a function of t. If you collect this alpha squared part and alpha beta part, there's 2 copies of fxy. That's where we use the continuity of the second order partials. So namely the Clairaut's theorem makes this fxy and fyx equal to each other. Then we have this restant part. So then we plug in t equals 0. This is what we wanted to know, the value of the second derivative at 0. So before you plug in t equals 0, there's supposed to be x and y there and x and y where to still have that line equation in it. But if you plug in t equals 0, that only picks up this alpha and beta part. So that's the value of the second derivative value at 0. So I'm showing you the lemma again. So we're looking at some sort of quadratic expression there where their alpha and alpha beta and beta showed up as something that is varying, and we have a fixed coefficient a, b, c there. So if you can guarantee that this coefficient have this condition and that condition there, we can guarantee that value is always a positive. So that's the situation. So have this lemma ready, and then let's compare it with what we have. So here's the situation, and we're about to use this lemma. That we got this expression of the special value of the second derivative at 0, and then it looks like this. So there's alpha squared and a beta squared, and those are x squared and x times y and y squared. We're looking at this as a coefficient in front of alpha squared and a beta squared and alpha times beta there. So we're going to set that capital A to be the second partial value, capital B to be whatever is in front of alpha beta, and C is coefficient of a beta squared. Then this really fit into that dilemma. So let's see if we have a condition. So first, this capital A was required to be positive, and we have that condition from the statement. So we have that condition. So let's look at the second part. The second part of the condition for that lemma requires b squared minus 4ac to be a negative number. Then this whole thing is going to be positive, and that's the conclusion of the lemma. So let's consider b squared minus 4ac here. So b squared will be 4. If you square that, it's 4, and then this value squared. And negative 4ac will be these two values, fxx and fy. So see if we have this quantity being a negative. If you look at the statement of the second derivative test, they stated fxx times fyy minus fxy squared, which is exactly opposite order. They assume that quantity to be positive. Therefore, this one must be negative. So with that condition, it really matches the condition required by the lemma. The A must be positive, and the discriminant, b squared minus 4ac, must be negative. So we have this condition in our lemma that guarantees that this quadratic polynomial in alpha and beta will be strictly positive, as long as alpha and beta is not at the same time 0. Here I'm showing everything now. We established this the part greater than 0 using the lemma, and one thing you have to be careful is that to get the strict positive condition, you must have the condition that not both alpha and beta is 0. And why is this case? Because alpha and beta is the directional numbers of a directional derivative, alpha can be 0 if you're pointing x directions or y directions, something like that. But these two cannot be both at the same time the 0. It's a vector. It must have unit length, and therefore it cannot be 0. So with this condition, we have strict positiveness of the second derivative because it's expressed as a quadratic expression like this, and we have this the sign condition so that the lemma guarantees that this is always a positive. So always here means that it doesn't matter what alpha and beta you're pointing at, every direction, that directional curve, will have a local minimum. So let me show you that statement again. So this was the main thing that we're using. We established the second derivative of one variable function is a positive and the first derivative 0. Therefore, along that curve is a local minimum. And as we change the direction to anywhere, it guarantees there's always keeping a local minimum condition. So altogether, as intuitively it's quite sufficient to conclude, all around is a local minimum in all directions. Therefore, it is a local minimum as a two variable functions. So that concludes the proof of this statement, which is just a part of the full second partial derivative, a second derivative test of a two variable functions. Again, the first derivative value is required to be 0, and there's this weird condition about the second derivative, and this really came from the discriminant of a quadratic polynomial. And with this leading coefficient condition, we guarantee that all around, all directional curve has local minimum. Intuitively, that's sufficient to conclude it's actually local minimum as a two variable function. Thanks.